Continuing on with the organic chemistry lecture series, we're continuing on with chapter 3, which focuses on alkanes and Newman projections. So first and foremost, let's provide an introduction to alkanes and hydrocarbons. So alkanes are hydrocarbons containing only carbon and hydrogen atoms connected by single bonds. Alkanes do not contain pi bonds. In other words, they don't contain double or triple bonds. The formula for a straight chain alkane is CnH2n plus 2, where N is the number of carbons. So for example, methane is CH4, where N is equal to 1. Ethane is C2H6. Propane, C3H8. Butane, C4H10, and so forth. Paying attention to the number of carbons and hydrogens is very important because, as we'll see later on, we can use the carbon and hydrogen count to identify the presence of double or bonds, triple bonds, or rings. Let's talk a little bit about alkane constitutional isomers. So normal alkanes, also known as linear alkanes, are alkanes with carbons connected to no more than two other carbons. For example, this 4-carbon straight chain alkane would be known as N-butane or butane, with N being the prefix for normal alkane. Branch chain alkanes are alkanes with one or more carbons connected to 3 or 4 carbons. So in this case, we have a branching substituent. Now, there's one last category of alkane that's going to become really important, especially in future chapters, which are these cycloalkanes. Cyclo, cyclic. Cycloalkanes are alkanes with carbons connected in a ring with a general formula of CnH2n. For example, cyclopropane is C3H6, cyclobutane is C4H8, cyclopentane C5H10, cyclohexane C6H12. Notice that compared to a traditional straight chain or normal alkane, cycloalkanes have 2 less hydrogens on account of the carbons being connected in a ring. You'll see that this will be very important later on. Okay, so let's talk now about naming alkanes and alkyl groups. So each alkane has a prefix matching the number of carbon atoms. Alkanes are indicated by the ane suffix. So here's a table of the different prefixes and different alkane names for different carbon counts. For example, a 1-carbon chain or group would have the meth prefix. A 1-carbon alkane would be methane. 2 carbons has the eth prefix. 3 prop, 4 bute, 5 pent, 6 hex, 7 hept, 8 oct, and so forth. Now, if you're naming an alkyl group, alkyl groups are given the YL suffix. So for example, a 1-carbon alkyl chain would be methane. A 1-carbon alkyl group would be a methyl group. So for example, if we had this 1, 2, 3, 4-carbon group, 4 is bute, so we'd name this as a butyl group. If this were the main chain, you can name it as a butane main chain. Cycloalkanes are given the cyclo prefix. To name a cycloalkane, you add the cyclo prefix to the name. For example, if we have a 3-carbon cyclic ring, it would be cyclopropane. 4 carbons, butane, In a ring, cyclobutane. 5 carbons in a ring, cyclopentane. 6 carbons, we're dealing with hexane. Since it's in a ring, this would be cyclohexane. Let's talk about some common names now of branched alkanes and branched alkyl groups. So alkanes can have multiple constitutional isomers for a given formula, and branched alkyl side chains are often given common names and prefixes, where some common prefixes you should know, the italicized I prefix is iso, T for tert, and S for seq. Here are some common side chains you want to be familiar with. Isopropyl, in this case, we have a propyl group where we're connected at the second carbon. Seq-butyl, a butyl group that is connected to the main chain at the second carbon. Isobutyl, which looks as follows. Tert-butyl, which is a 4-carbon group, in which case here you have a highly substituted quaternary carbon. A tert pentyl group, which is a variation on the tert butyl group. You're going to want to be familiar with each of these common branched alkanes and their names, as they come up a lot in terms of alkane nomenclature. We'll also talk about alternative ways to name these branched alkyl groups, but the common names are highly referenced and they're very efficient for naming these complex branch side chains. Let's talk a little bit about naming alkanes, starting with the principal idea, which is naming the parent chain. Alkanes are named based on the longest, most branched parent chain. In this rule, you're going to select the longest chain and the chain with the most branching. So for example, if we look at and we compare two possible ways to name the following compound, we're going to select the following chain as the parent chain because it has 1, 2, 3, 4, 5, 6 carbons. So it's the longest chain. So this would be a hexane main chain. We'll talk a little bit about how to construct the full name, but just for your reference, this would be 2,3-dimethylhexane. Now, in the event you have two chains with the same carbon count, such as in this case, we have the choice between 2 carbon chains for the same compound. And in this case, the 2 carbon chains that we've drawn out as the longest main chain have the same carbon count. The tiebreaker in this case is branching. The most branched chain has the most substituents. So in this case, we have 1, 2 substituents. In the second case, we just have 1 substituent. So in this case, the numbering method and the main chain outlined on the left is preferred because it has the most branching. So this would be named as 3-ethyl 2-methylhexane instead of 3-isopropylhexane. So again, when selecting the parent chain, you select the longest chain first, and then as a tiebreaker, you pick the longest chain with the most branching. Now, there's a trick in order to identify the longest chain. What you're going to do is you're going to start counting from the end of the longest substituent chain. And at each branch, you're going to count towards the longer chain or the most substituted chain in the event of a tie. So to give you an example, let's look at the following worked example. So in this case, we have multiple substituent side chains. In this case, let's take a look and let's talk a little bit about each of the side chains here. First and foremost, 1, 2, 3. 1, 2, 3. 1, 2, 3. So in this case, we can pick any of these side chains here to start counting down. Our goal is to get the largest carbon count for our main chain. So starting at the bottom, we count 1, 2, 3, 4. We have two choices. We can either count towards a 1-carbon chain or a much longer chain. So we're going to go to the left. We're going to count 5. Now in this choice, we have a 3-carbon chain and a 3-carbon chain. We're just going to count up arbitrarily. You can also count to the left. Both will give identical carbon counts and identical branching. So we have 6, 7, 8, 6, 7, 8. So our longest chain in this case will have 8 carbons and will be an octane chain. Next, we're going to name the side groups. So this group has 1 carbon, so it will be named as a methyl group. This side chain is a 3-carbon side chain, so we'll name it as a propyl group. We'll talk momentarily about how to assign the locant numbers and how to assign the position of each of our substituents. For your reference in this case, this compound would be named as 4-methyl 5-propyl octane. For now, we're just going to focus on identifying the longest chain, the parent chain, and naming the substituents. So I'd like you to pause the video at this time, and I'd like you to work through these next 3 examples, and we'll discuss momentarily. Okay, so first and foremost, looking at our chain length, we have a 2-carbon, 1-carbon, 2-carbon chain. So I'm going to start at the end of one of our 2-carbon chains. I'm going to count 1, 2, 3. Now I have a choice between 1-carbon and 2-carbon side chain, and I'm going to count up towards the 2-carbon side chain because we want to count towards the longest overall chain length. That gives us 4, 5. So in this case, we have our longest chain, which has 5 carbons. So this would be a pentane main chain. And then to name this 1-carbon group, this will be a methyl group. Writing the full name, this will be 3-methyl pentane. Looking at this next case, we have a 2-carbon chain, a 2-carbon chain, a 1-carbon chain, and a 2-carbon chain. You can also think of this entire chunk at this juncture as 3 carbons. So in this case, we are going to count down our longest chain. And since this chunk here is 3 carbons, we're going to start counting down. 1, 2, 3. We have a choice between 1 carbon and way more than 1 carbon. So we're going to count to the right. 4. Now we have a choice. They're both 2-carbon chains, but this one is more branched. So we're going to count towards the more branched chain, 5, 6. So this in turn gives us 1, 2, 3, 4, 5, 6, a 6-carbon chain. So this would be a hexane main chain. And now all we have to do is name our side chain groups. So in this case, we have a 2-carbon side chain here, a 1-carbon side chain, and 1-carbon side chain. So we have a methyl group, and then this group here would be an ethyl group. Now, the numbering method that I'm going to explain to you now and show you now here, we're going to discuss later on, but I do want to provide you the full name for reference. In this case, given that we have a 6-carbon chain, we're going to name and number these substituents. So in this case, this would be 3-ethyl, 2,4-dimethyl hexane. For now, you just need to be able to identify the longest chain and name your substituents. Okay, looking at this last example here, we have a 1, 2, 3 carbon chain with some branching, a 2 carbon chain, and a 3 carbon chain with some branching. So in this case, we can pick either of the 3 carbon chains to count down. 1, 2, 3, 4. Okay, now we have a choice. We can count right or left. 3 is much bigger than 2, so we're going to count to the left. 5, 6, 7. Okay, so in this case, we have a 7 carbon main chain. Now let's identify and name our substituents. So here we have a propyl group connected at the 2nd carbon. This is an isopropyl group. And then we have 1, 2 methyl groups. So this is one of the rare cases where we have a branched substituent that's named as a substituent, because in this case we have a longer chain by counting in the other direction. So then, putting this together, we would name this as 4-isopropyl 2,5-dimethyl. And because we have a 7 carbon chain, this would be heptane. So this would be 4-isopropyl 2,5-dimethyl heptane. So this method of counting down the longest chain, and each time you hit a juncture, you count towards the longer chain, is a generally quick and efficient way to identify the longest chain with the most branching. One other rule of thumb that's important to note is that the cycloalkane is generally the parent chain if the attached carbon chain has less carbons. So for example, in this case, this compound will be named as methyl cyclopentane. This compound, looking at the side chain here, we have a 6 carbon cycloalkane and a 2 carbon side chain. This is an ethyl group, 6 carbons, cyclohexane, main chain. So this would be named as ethyl cyclohexane. Looking at this last case, we have a 4 carbon cyclic hydrocarbon, and our side chain has 3 carbons. So we would name this as propyl for this 3 carbon side chain, which is known as a propyl group. A 4 carbon ring would be cyclobutane. Okay, let's keep going now, and let's talk a little bit about naming alkanes following IUPAC naming rules. IUPAC names, which is the systematic naming guideline to name organic compounds, these names are divided into 4 parts: the substituents, the prefix, the main chain name, and the suffix. For example, 2-ethyl cyclohexane, 2-ethyl are the substituents, cyclo is the prefix, the main chain is hexane, and the suffix is ane. So this is telling us that we have a 6 carbon alkane that's arranged in a ring with an ethyl group at the 2 position. Now, when naming alkanes, you're going to follow the following systematic approach. First, you write the name of each substituent in alphabetical order. For example, ethyl goes before propyl alphabetically. You're going to include the locant number in front of each substituent. For example, 2-methyl. You're going to also include the prefix and locant numbers for each substituent. So for example, if you have a branch chain, or if you have multiple of a given substituent that requires a prefix, you'd include the prefix, such as an example 2,3-diethyl and 2-tert-butyl. You're going to want to make sure when you're writing the full name for the compound that you write the name of the main chain, including the prefix and the suffix. So for example, pentane. The full name, 2-methylpentane. This first part denotes the substituent and their location. The last part denotes what kind of main chain do we have and what substituents in terms of functional groups are found on the main chain. Now, we've talked a little bit about locant numbers. Let's elaborate on that. So to name alkanes, the first thing that you need to do is you need to name and identify the main chain, which is the longest, most substituted chain. Now, when you number the main chain, for example, if you have a chain, you can count in two directions, from left to right along the chain or from right to left. These give what are known as locant numbers, which are the location of substituents on your chain. So when you number the main chain, atoms from end to end, left to right and right to left, you'll have two sets of locant numbers. You're then going to assign locant numbers to each substituent. For example, in 2-methylbutane, we have 1, 2, 3, 4. This is one method of writing locant numbers. The other set would be counting from right to left. Now, when we have a substituent such as this methyl group, we have a choice of numbering it with the locant number 2 versus 3. We're going to use the set of locant numbers with the smallest locant number for the first substituent. So because 2 is less than 3, we're going to use the locant number set 1, 2, 3, 4, counting from left to right. So this will be named as 2-methylbutane. 2-methyl because there is a methyl group at the 2 position, butane because we have a 4-carbon chain. Let's apply what we've learned to this next example. So I'm going to number and identify the longest chain. In this case, we have a 2-carbon, 2-carbon, and 2-carbon chain. So we count down 1, 2, 3. If we have a choice, we choose the chain with the most branching. So we're going to count up and to the right, giving us 4, 5. So we have our longest chain. Now there are two methods of counting down the longest chain, left to right and right to left. Okay, so from here now, we have to look at the two possible locant numbers for our two possible substituents. This substituent is a methyl group. This substituent is an ethyl group. And let's take a look at our two possible numbers. So in this case, we have a choice between 3-ethyl, 4-methyl versus 2-methyl, 3-ethyl. So in this case, we're looking for the smallest locant number for the first substituent. 2 is the smallest locant number, so we're going to choose this numbering method. Arranging this in alphabetical order, ethyl goes first, so we name this compound as 3-ethyl, 2-methyl, and then finally, because we have a 5-carbon main chain, 5 carbons would be pentane. So this would be 3-ethyl, 2-methylpentane. Again, you'll want to choose the set of locant numbers that gives the smallest locant number for the first substituent. Importantly, when a branch or substituent occurs more than once, you prefix the name with di, tri, and tetra. For example, in this case, we see that we have 1, 2, 3 methyl groups. So we would name this as 1, 2, 3, 4, 5, 6, 7. we would name this as 2,5,5-trimethyl. In this case, the full name would be 2,5,5-trimethyl heptane. Heptane because we have a 7-carbon chain. Now, notice, part of the reason why we named this as 2,5,5 instead of 3,3,6 is because 2 is the smallest starting locant number. And when we pick carbon locant numbers, we choose the set of locant numbers with the smallest locant number for the first substituent. And 2 obviously is less than 3. Let's talk about naming alkanes following IUPAC rules in the event of a tie. If there is a tie, you compare the locant numbers for the second substituent, and you repeat looking at the third, fourth, and fifth substituent until the tie is broken. So for example, in this case, we have a few possible sets of locant numbers. We can count from left to right, 1, 2, 3, 4, 5, 6, or we can count from right to left, 1, 2, 3, 4, 5, 6, 7. Okay, now, in this case, we have a choice. We can name this using the locant numbers. So there are a few possible comparing these two locant number sets. Just to make sure that the cross-out matches. In this case, the 2, 3, 6 labels occur if we count from right to left. So we have 2, 3, and 6 for our methyl locant numbers. We count from left to right, we get 2, 5, and 6 for our locant numbers. So first, 2 and 2, we end up with a tie. Then we compare the next locant number, 3 versus 5. 3 is less than 5. So we're going to use the numbering method on the left because it gives us the smallest locant number for each substituent sequentially. For the first substituents, we see both the methyl groups are with locant number 2. We look at the next substituent in line. We have locant number 3 versus 5. 3 is less than 5. So we number using the numbering method on the left. So we name this compound as 2,3,6-trimethyl heptane. Let's apply what we've learned now to this structure on the right. So you may want to pause the video at this time and work through the following example, and then we'll discuss momentarily. Okay, so first and foremost, identify the longest chain. We have 2 carbon chains on the left, so I'm going to count down one of them arbitrarily. 1, 2, 3. I have a choice between a 2 carbon chain and a much bigger chain, so I'm going to count down the larger chain. 4, 5. We have a 1 carbon side chain versus something that's much bigger than 1 carbon, so I'm going to keep counting. And these are 2 carbon chains. We can count in either way and be fine. This gives us an 8 carbon main chain, which is octane. Let's now look at our alternative set of numbering. So we counted from left to right. Let's count from right to left. 1, 2, 3, 4, 5, 6, 7, 8. Let's now list out our possible locant numbers. So looking at the counting from left to right, the numbering in black, we have 3 ethyl, 5 methyl, and 6 ethyl. So we have 3, 5, 6. Looking at the numbering method in blue, we have 3 ethyl, 4 methyl, 6 ethyl. So in this case, looking at the first substituent, we have a tie. For the second case, second locant number, 4 is less than 5, so we're going to use the numbering methods in blue. Now, in terms of cleaning this up, we have two ethyl groups. So we'll combine them together with a di prefix. So we'll name this as 3,6-diethyl 4-methyl octane. Okay, so as you can see, when you encounter a tie in the first locant number, move to the next locant number, and then you keep repeating until the tie is broken. You want to select the lowest locant number for each substituent sequentially. Let's now talk a little bit about alphabetical order rules. One other way to break a tie is if there's a tie, you're going to assign the smallest locant number to the first substituent alphabetically. Iso and cyclo prefixes count for alphabetization. Ignore di, tri, tetra, neo, and tert prefixes. The only prefixes that are considered for alphabetization are iso and cyclo prefixes. For example, in this case, 1, 2, 3, 4, 5, 6, 7, 8. This compound is named as 4-ethyl 5-methyl instead of 5-ethyl 4-methyl. The reason why we choose to give the ethyl group the lowest locant number is because ethyl is first alphabetically and the locant numbers are otherwise identical between these two compounds. In the event of a tie that's not broken on the basis of lower locant numbers, you break the tie using alphabetical order. And because ethyl's first alphabetically, ethyl gets the lower locant number preferentially. So we name this compound as 4-ethyl 5-methyl octane. Let's apply what we've learned now to the following example. You may want to pause the video to work on this example, and we'll discuss this example momentarily. Okay, so let's identify the longest chain. We have 2 carbon chains on this side, a 2 carbon chain on this side. I'm going to count down this chain. 1, 2, 3. I'm going to count towards the longer chain. 4, 5. 2 carbons, 2 carbons. The chains are the same length. We can count in either direction. Let's now count, since we counted from left to right initially, let's count from right to left. Okay, so now let's take a look at our substituents and let's note the locant number. So in this case, we have 3-methyl 5-ethyl using the numbering method in black. And then we have 3-ethyl 5-methyl using the numbering method in blue. Locant numbers are identical. We now move to the alphabetical order tiebreaker. Ethyl is first, so we'll use the numbering method in blue. So we'll name this as 3-ethyl 5-methyl 7-carbon chain. That would be heptane. Again, only resort to the alphabetical order tiebreaker if there's a tie in all of the locant numbers. Let's talk a little bit about alphabetical order rules and prefixes. Please note the iso and cyclo prefixes count for alphabetization. All the other prefixes do not. For example, the following compound is named as 3-ethyl 5-methyl heptane, as we saw from the example that we just did. Let's take a look at another representative example. This time we have a branched side chain. So in this case, identifying the main chain, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have 2 possible numbering methods. In this case, we have a group at the 4 position. This is an isopropyl group. Iso is included in alphabetization. and then we have 5-ethyl. In blue, we have 4-ethyl, 5-isopropyl. Ethyl is first alphabetically, so we name this compound as 4-ethyl, 5-isopropyl, 8 carbons, which would yield octane. Let's try to apply what we've seen to this next example. So you may want to pause the video, and then we're going to be discussing this example pretty much right now. Okay, so numbering. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so in this case, using the numbering method in black, we have 3,3-dimethyl, 6-ethyl. Looking at the numbering method in blue, we have 6,6-dimethyl, 3-ethyl. In this case, E is first alphabetically. So in this case, this compound will be named as 3-ethyl 6,6-dimethyl octane. Again, remember that the di, tri, and other prefixes are not included in terms of alphabetical order. So let's keep going now, and let's look at what happens when we're naming cycloalkanes and other complex substituents. So cycloalkyl groups are going to be the main chain if they have more carbons than the substituent chains. Cycloalkanes are given the cyclo prefix. In this case, you'll number the carbons counting around the ring, either clockwise or counterclockwise. And again, you're going to select the locant numbers that give the lowest locant number for each substituent sequentially. So for example, this compound here will be named as 1-ethyl 3-methyl cyclopentane. We're counting clockwise around the ring rather than counterclockwise. Why? If we counted counterclockwise, we'd end up with 1,4 instead of 1,3 as our locant numbers. By the same token, looking at the following cycloalkane, we can number it starting with one of the methyl groups, 1, 2, 3, 4, 5, 6, or we can count counterclockwise, 1, 2, 3, 4, 5, 6. Using the numbering method in black, we end up with locant numbers of 1, 2, 4 versus the locant numbers of 1, 4, 6. In this case, the locant numbers in black are the lowest possible locant numbers. Now, you could try changing which carbon you start counting clockwise or counterclockwise from, but in this case, counting 1, 2 will give us the lowest set of the first two locant numbers. One alternative would be to count from this carbon here, 1, 2, 3, 4, 5, 6. But again, 1, 2, 5 is not a lower set of locant numbers than 1, 2, 4. So this compound would be named as 1, 2, 4 trimethyl cyclohexane. Now, some interesting things can happen if the parent chain has more carbons. In this case, cycloalkyl groups are named as a substituent. For example, this compound would be 3-cyclopropylpentane because we have a 5-carbon main chain, which is greater than this 3-carbon side chain. Given that, how would you name the following compound, which has 1, 2, 3, 4, 5, 6 carbons, and we have this 4-carbon ring as a side chain? In this case, we'd name this as 2-cyclobutyl, cyclobutyl, cyclo, ring, butyl, 4 carbons, and then hexane for the main chain. So 2-cyclobutyl hexane. Let's talk a little bit about complex substituents. Now, branch substituents, in addition to being named using a common name, for more complex branch substituents, you can name these branch substituents using IUPAC rules. In this case, you number the atoms from the substituent, starting from the carbon attached to the main chain and moving away to the main chain. For example, this substituent, we pick the carbon attached to the main chain as carbon 1, and we count away from the main chain. You name the substituents on the side chain and number the side chain substituents based on their carbon number in the side chain. If a substituent has a common name, please just use the common IUPAC name. For example, in this case, this side chain here would be a 2-methylbutyl side chain. 2-methyl because the methyl group's at the 2 position on the side chain, butyl because it's a 4-carbon side chain. So overall, this would be 6 because this side chain's at position 6 on the main chain, 2-methylbutyl undecane. Applying what we've learned, take a moment, pause the video, and work on this next example, and we'll discuss it momentarily. Okay, so first and foremost, the carbon attached to the main chain is carbon 1, followed by carbons 2 and 3 counting away from the main chain. We see in this case, we have methyl groups at positions 1 and 2. So this would be a 1,2 dimethylpropyl group. And then this is attached to a 5-carbon ring. So this would be 1,2 dimethylpropyl cyclopentane. We don't need to note the position of this substituent in this case because the name implies we just have one substituent attached to the cyclopentane chain. You don't need to say it's 1,2-dimethylpropyl because if there's only one substituent, all of the positions are functionally identical on the cyclopropane ring in terms of naming. This is part of why I encourage you to be familiar with the common names because it allows you to avoid having to name a substituent using these more complex IUPAC rules. Let's now practice naming alkanes by drawing structures from IUPAC names. Drawing structures from an IUPAC name is very straightforward. It's almost like assembling a Lego set following some instructions in that the name tells you exactly how to put together the structure. First, you draw the main chain, and if the name includes substituents, you add the substituent to the indicated locant number. For example, 3-ethyl 2-methylhexane. Hexane, draw a 6-carbon chain. 1, 2, 3, 1, 2, 3, 4, 5, 6. Next, 3-ethyl. 1, 2, 3. Position 3 gets an ethyl group, which is 2 carbons. Position 2 gets a methyl group, 1 carbon. There we go. All done. Let's look at this next example. 1-ethyl 3-isopropyl cyclopentane. Cyclopentane, 5 carbons, cyclo in a ring. Ethyl group at the 1 position, 2-carbon side chain. Isopropyl at the 3 position. Isopropyl, it looks like a propyl group except we connected at the 2 position. So we have 1-ethyl 3-isopropyl cyclopentane. As you can see, one of the benefits of the IUPAC naming convention is that it allows you to very quickly draw the structure from the name. Let's now practice this skill. I'd like you to take a few moments and I'd like you to draw the structure given the following names. So pause the video at this time and we'll discuss this example momentarily. Okay, so 2,3,5 trimethyl heptane. Heptane, 7 carbons. So 1, 2, 3, 4, 5, 6, 7. 2,3,5 trimethyl, we need a methyl group at positions 2, 3, and 5. And there we go. That's all you have to do in terms of putting together the structure from the name. Here we have a complex substituent. Nonetheless, let's start with our main chain, hexane, 6 carbons. 1, 2, 3, 4, 5, 6. We next need a methyl group at position 2. And at position 3, we have a 2-methyl ethyl group. So in this case, we have an ethyl group side chain. This should be 1-methyl ethyl. 2-methyl ethyl would just be named as propyl. Because given the numbering convention 1, 2, if we just put a methyl group at the 2 position, this would just be a propyl chain. 1-methyl ethyl would be named and written out as follows. 1-methyl ethyl is an alternative name for an isopropyl group. So in this case, it's important to be familiar with the complex IUPAC naming, as sometimes the complex IUPAC name is used in place of the common name. Let's take a look at the following next examples where we're asked to name the following compounds. So I'd like you to pause the video, take a few moments, and then we'll talk about these examples momentarily. Okay, so in this case, we have a cyclohexane, 1, 2, 3, 4, 5, 6, 6 carbons. So this is cyclohexane. This group here has a special name. This is a cycbutyl chain. This chain is methyl. B is first alphabetically, so we will in turn prioritize giving the cycbutyl group the lowest locant numbers. So we name this as 1 cycbutyl, 2 methyl cyclohexane. Looking at this next example, we have 2 possible sets of locant numbers. In this case, we have the choice between 2,3-dimethyl, 5-ethyl versus 3-ethyl, 5,6-dimethyl. In this case, locant number 2 is the smallest possible starting locant number. So we're going to start and use the numbering method and locant numbers in black. So this will be named as 5-ethyl. 2,3-dimethyl. And because this is a 7-carbon chain, it would be heptane. Okay, so now we've seen and covered IUPAC naming for alkanes extensively. What we're now going to do is we're going to move on to analyzing and visualizing three-dimensional structure and molecular shape using Newman projections and dash wedge notation. So in this case, I would highly encourage you to have a model kit available for these next examples and for you to try building the models presented in each of the photos for each of the structures we're going to discuss. So in terms of molecular shape, dash wedge notation is a critical way of describing molecular shape. We use dash wedge notation to describe the three-dimensional shape of tetrahedral carbons, sp3 carbons. A wedge implies the substituent points up and out of the page towards us. A dash implies the substituent points down and into the page, away from us. So for example, in the following, we see that chlorine has a wedge. And as you can see, this chlorine atom is pointing out of the page towards us. In a 3D view, the chlorine is pointing towards us. By the same token, the hydrogen with a dash is pointing away from us, into the page. If you're viewing this from a side-on perspective, the chlorine is pointing more towards us because it's wedged, while the hydrogen with a dash is pointing away from us. Another perspective here is, in this case, as we see, the bromine has a wedge, and as you can see from the three-dimensional model, this sphere, which corresponds to the bromine atom, is pointing right towards us. The hydrogen, which has a dash, is further in the back, pointing away from us. Anything with a normal straight line is considered part of the plane of the page. So you can consider it like the chlorine and fluorine are drawn perfectly flat on the page. Now, as discussed, substituents drawn with a normal line are on the plane of the page. And I would recommend whenever you encounter a dash wedge structure to use a model kit. And to make sure you're assembling these structures correctly, you may want to check and compare to the structure photos provided in the notes. Now, one thing I also need to be very clear with, a given dash wedge structure is just one way of viewing a molecule. There are many, many ways to view the same molecule. And as such, it's really important that when you make a model, you make sure that the model is assembled correctly and that you always keep in mind that there are many ways to draw the same molecule depending on your perspective. As we've seen in these photos, we can look at our molecule from different perspectives and see how it maps on to a given dash wedge depiction of that molecule. Okay, let's talk a little bit about Newman projections and conformations. Carbon-carbon single bonds are rotatable, so molecules can adopt multiple conformations by bond rotation. So this carbon-carbon bond can be rotated, and as such, we can access multiple unique conformations as a result of bond rotation. What is a conformation? It's a 3D arrangement of atoms for a given molecule as the result of bond rotation. So for example, if we have a carbon-carbon bond and we rotate that carbon-carbon bond, we can in turn access a different conformation with a different arrangement of atoms in three-dimensional space. Now, a Newman projection is a 3D drawing looking down a carbon-carbon bond. So for example, if I took my eye and I stared down this carbon-carbon bond, I would see what's known as a Newman projection. The front carbon is drawn in the front, the back carbon is not visible, and the substituents are drawn for the front carbon in front of the circle. In the back carbon, those substituents are drawn in the back of the circle. We will talk more about Newman projections. I just want you to get this general idea that Newman projections, you're looking down a carbon-carbon bond. And that's why the back carbon is not visible. A sawhorse representation is a 3D drawing looking at a carbon-carbon bond from a 45-degree angle. So for the sawhorse projection, you're looking at it almost from the side-on view. Why do we care about the sawhorse projection? Sometimes it lets us see things that are more difficult to see in the Newman projection. Okay, let's talk now about the mechanics of drawing Newman projections. Newman projections are a critical way to succinctly visualize different conformations around carbon-carbon bond rotation, and as such, it's important to be very familiar with how to draw Newman projections. So first, you're going to need to draw a full Lewis structure for your molecule, including all of the carbon-hydrogen bonds, and making sure to include any dash wedge information if it's given in your structure. Next, you're going to select the bond you're going to view. Newman projections are drawn looking down a specific bond, and as such, it will often be clearly stated in any problem what bond you're looking down. Generally, if you have a choice, try to pick the bond with the most substituents because that's usually the one that has a lot of the information that you're looking for in terms of reactivity, etc. So for example, I've picked this bond. So this carbon-carbon bond is the one that I care about. And now I'm going to look down this carbon-carbon bond from left to right. So this is the carbon that's going to be in the front, and this is the carbon that's going to be in the back. Another way to think about it, if I'm using numbering, I'm looking down the C2, C3 bond using this numbering convention. So I'm looking down with carbon 2 in the front and carbon 3 in the back. It's important to be really clear about your perspective to keep things from getting mixed up. So here is a model of this molecule. One thing I'd like you to note, the chlorine has a wedge and the chlorine is pointing towards us. The bromine has a wedge, the bromine's pointing towards us. The hydrogens, which have a dash, are pointing away from us. One thing that you could see almost is that from our view, all the dashed structures are in the back of our view, all the wedge structures are in the front of our view. You'll see why this is important in a moment. Now, in order to look down this carbon-2, carbon-3 bond, right now we are staring at it, at this entire model from the side. I want to look down carbon-2. So what I'm going to do is I'm going to turn my model, rotate my model 90 degrees, so that the, in this case, left carbon is in the front. So carbon-2 is right here. We're going to rotate our structure 90 degrees. In this case, rotate it 90 degrees to the left. So carbon-2 is now in front. Now, one thing I'd like you to pay attention to is that all of the wedge substituents ended up on the right. All of the dash substituents ended up on the left in this new view. So as you can see, chlorine and bromine, after rotation 90 degrees to the left, we now see we have chlorine and bromine, the wedge substituents on the right, the dash substituents on the left. Okay. The other thing that I'd like you to note is if we take a look at our carbon-carbon bond here, this CH3 group is above this carbon-carbon bond. This CH3 group is below. We'll say above is up, below is down. I'd like you to notice how, let me just put a star next to this CH3 group. This CH3 group has ended up here. Do you notice how it is pointing down, as in pointing towards the bottom of the page? While at the same point, the CH3 group that was above pointing up ends up pointing up towards the top of the page. I'd like you just to be aware of this because it'll make it a lot easier to draw the Newman projection and keep things sorted. I would recommend using a model kit to draw Newman projections until you start to get familiar with how to manipulate structures using just pen and paper. Using a model kit is critical to developing this skill set. Okay, now that we have our rotated view, the front carbon is represented by a circle. Each substituent is drawn 120 degrees apart. The back carbon is behind the circle, and each back substituent is drawn from the circle edge. You're going to start by drawing the line substituents pointing up or down, then you're going to add the other substituents. So, for example, in this case, this methyl group here is pointing down. This is our front carbon, C2, which is in the front. This is C3, which is in the back. For the front carbon, I have a CH3 group. This front carbon, our substituents are drawn in front of the circle. And I have a CH3 group pointing down. Next, drawing what I see, and if you have a model, you really can just draw what you see. The CH3 group is pointing down. The chlorine is pointing up and to the right. The hydrogen on the front carbon is pointing up and to the left. Let's now look at our back substituents. This CH3 group is pointing up. So we draw the CH3 group on the back carbon pointing up. Next, we have the bromine on the back carbon, which is pointing down and to the right. And then the hydrogen on the back carbon, which is pointing down and to the left. Okay, as you can see, for the front carbon substituents, they are drawn in front of the Newman projection circle. The back carbon substituents are drawn from the circle edge to represent the fact that they're attached to the back carbon. Now, as we've noticed in this case, all of the wedge substituents ended up on the right, all of the dash substituents ended up on the left. And this maps on to what we see in our final Newman projection. So when you generate a model and rotate the model so you're looking down the indicated carbon-carbon bond, it becomes very easy to generate a Newman projection. Once you have your model properly rotated and you're looking down the carbon-carbon bond, you can really just draw what you see. And this is why I encourage you to use your model kit. Now, let's talk about drawing Newman projections rotated. Let's, in this time, so if we have C2, C3 bond, let's look down the bond from the C3 to C2 perspective, this time with carbon 3 being in front. Again, we start with our original model, and we start making sure that the dash wedge depiction matches our model. Chlorine's in front, bromine's in front, everything looks good here. So, if we want the atom on the right, which is carbon 3, to be in front, we rotate the molecule 90 degrees to the right. This in turn means that carbon 3 is now in front. Interestingly, in this case, everything with a wedge ends up on the left, everything with a dash ends up on the right. It's very easy to visualize this rotation if you use a model kit. Here's what the model will look like after rotation. I would like you to compare to your own model kit. As you can see, the bromine and chlorine are on the left, the two hydrogens are on the right, carbon 3 is in front, and carbon 2 is in the back. The other thing I'd like you to note again is this methyl group on carbon 3 is above our bond line, and it ends up pointing up and above the bond line in the Newman projection. Likewise, the carbon 2 carbon is pointing down below the bond line, and this CH3 group attached to carbon 2 is below the bond line. Now we just draw what we see. On the front carbon 3, we have the methyl group pointing up, the bromine pointing down and to the left, hydrogen pointing down and to the right. On the back carbon 2, we have a methyl group pointing down, the hydrogen pointing up and to the right, and the chlorine pointing up and to the left. Note, I tilted the view a little bit so you could see carbon 2. In the actual Newman projection, you never draw the back carbon. Okay, so here's a cheat sheet. One thing that I'd like you to keep in mind for this cheat sheet is it assumes that you're looking at your molecule from the left to right perspective, that you're looking down the carbon on the left towards the carbon on the right. I would encourage you to reference this cheat sheet, but I would note the most definitive way to draw the Newman projection would be to make a model. So let's do some examples. We're asked to draw the Newman projection for each molecule, viewing down the indicated atom and bond. I'd like you to pause this video and we'll discuss these next two examples momentarily. Okay, so starting with this case here, in this case we have this diol and we're asked to look down the following carbon-carbon bond. I'm going to label this as C2 and C3. So, first and foremost, what we can do if we're looking down this bond, we're going to rotate this structure 90 degrees. And I'm going to show you what this looks like on pen and paper. I would like you to make a model and do this manipulation using your model kit, just like we've discussed earlier. So in this case, if we rotate this structure 90 degrees to the right, we have carbon 2 in front. The alcohol, which has a wedge, ends up on the left. The hydrogen, which has a dash, ends up on the right. The methyl group, which is pointing down, still ends up pointing down. The other alcohol, which has a wedge, ends up on the left, same side as the other alcohol with a wedge. Hydrogen ends up on the right. The methyl group ends up pointing down. Looking down the C2-C3 bond, with C2 as my front carbon, the methyl group is pointing down. The hydrogen is on the right. The alcohol is on the left. Looking in the back, we have a methyl group pointing down, the hydrogen on the right, and the alcohol on the left. Now, it's really important that you do not accidentally draw the mirror image of your structure. That is a different type of compound entirely, which we'll talk about in future chapters. So just make sure to retain the correct bond connectivity. Let's look at this next example. In this case, we are looking down the following carbon-carbon bond, this time from left to right. Now, because I'm looking down from left to right, I can use the cheat sheet here. So let's see if I can find the cheat sheet depiction that matches what I'm trying to draw. Okay. This looks like it matches. So in this case, drawing out and adding the hydrogens here. If we're looking down C2, C3, if C2 is in front, everything with a wedge ends up on the right. So the hydrogen ends up on the right. The amine, which has a dash, ends up on the left. The methyl group, which is above the bond line, is pointing up. On the back carbon, the methyl group is also pointing up. The chlorine has a wedge, so it's on the right. The hydrogen has a dash, so it's on the left. It would be reasonable to make a model kit to verify that this cheat sheet is working as intended. So here are two methods to draw Newman projections. And again, I would encourage you to make a model for each of the structures outlined to help you visualize these carbon-carbon bond rotations and adjusting your perspective. So why do we care about this? Well, when we talk about different conformations, not all conformations are the same in energy. And often to understand a structure, we have to perform what's known as conformational analysis. In conformational analysis, we're going to be analyzing the relative energy of each conformation of a molecule. We do not observe perfectly free bond rotation. Conformations have different energy. And as conformations have different energies based on dihedral angle, there is a barrier to rotation. What is dihedral angle? It is the angle separating two atoms looking down a bond. For example, if we're looking at the ABCD atom bond, this dihedral angle is the separation between two atoms looking down a bond. In this case, this would be a 180-degree dihedral angle, while in this case, we would have a dihedral angle of 0 degrees. Now, we provide and we give certain conformations specific names. The staggered conformation is a low energy conformation where there's a 60-degree dihedral angle and the bonds are as far apart as possible. As you can see here, we have a dihedral angle of 60 degrees. In the eclipsed conformation, it's a high energy conformation with a 0-degree dihedral angle and the bonds are as close as possible. As you can see, this dihedral angle is 0 degrees. Now, how do we quantify the differences in energy between conformations, and what is the cause of this difference in energy between conformations? Well, torsional strain is a huge culprit, where torsional strain is defined as the energy difference between the staggered and eclipsed conformations. For ethane, the torsional strain is 12 kilojoules per mole. In other words, 4 kilojoules per mole for each hydrogen-hydrogen eclipsing interaction. Now, you may wonder, what is the actual physical meaning behind torsional strain? It really represents the fact that the staggered conformation is lower in energy due to what's been determined to be a stabilizing interaction between the carbon-hydrogen sigma bond and adjacent carbon-hydrogen antibonding orbital. So the best way to phrase torsional strain isn't that necessarily the eclipsed conformation is destabilized, but rather the staggered conformation is preferentially stabilized by this effect. So in the staggered conformation, looking at it from a side-on perspective, you're able to get donation from this carbon-hydrogen sigma bond into the carbon-hydrogen sigma star antibonding orbital, and this is a stabilizing interaction. And this is only present in the staggered conformation. So, key takeaways here: staggered conformation, generally going to be lower in energy. Torsional strain is the energy difference between staggered and eclipsed conformations. And generally, the eclipse conformation is going to be higher in energy, in part because it doesn't have this stabilizing interaction, and because as we start to change substituents, we start to introduce another type of interaction known as a steric interaction. So let's look at some simple case studies here. Let's look at ethane for a moment. For ethane, there is one unique eclipse conformation and one staggered conformation. Ethane looks like this. C2H6. As you can see, as we rotate our carbon-carbon bond and we observe the Newman projection down the carbon-carbon bond, we see that there are really only one unique staggered and one unique eclipse conformation. The difference in energy between staggered and eclipse conformations is 12 kilojoules per mole, or 4 kilojoules per mole for each hydrogen-hydrogen eclipsing interaction. We can make what's known as a conformational analysis diagram where we can look at potential energy as a function of dihedral angle. And because we only see the energy maxima and minima in 60-degree bond rotation increments, what we can do is we can take our given Newman projection, we rotate the carbon-carbon bond 60 degrees, and then we observe the strain present in the new conformation. So we rotate our carbon-carbon bond 60 degrees, and we observe the resulting conformation. Now, let's look at propane. For ethane, there is one unique eclipsed conformation and one staggered conformation. When we elaborate to propane, which looks like this, the only difference here is that we now have this methyl group. As such, if we take a look at propane, the only thing that changes between ethane and propane is the introduction of this methyl group. Rotating and looking at various conformations by rotating our carbon-carbon bond 60 degrees, we notice that there are two major conformations, the staggered conformation and the eclipsed conformation. And there is really only one unique staggered conformation and one unique eclipsed conformation in propane, just like we saw for ethane. In terms of torsional strain, the torsional strain is 4 kilojoules per mole for the hydrogen-hydrogen interaction and 6 kilojoules per mole for the methyl-hydrogen interaction. So this methyl-hydrogen eclipsing interaction is 6 kilojoules, while a hydrogen-hydrogen eclipsed interaction is 4 kilojoules. In total, the difference in energy between the staggered and eclipsed conformations of propane is 14 kilojoules per mole. This represents the barrier to rotation. The difference in energy the energy barrier that must be surmounted to rotate your carbon-carbon bond and get this higher energy conformation is 14 kilojoules per mole. The larger the barrier to rotation, the more difficult it is to surmount the barrier and effectively rotate your carbon-carbon bond and access potentially some of these higher energy conformations. Okay. For those wondering why is the methyl hydrogen eclipsing interaction introducing much more strain, the methyl group is larger and we're starting to see what's a little bit of a steric effect at play. The methyl group extends into a wider region of space, and thus, when it starts to bump into adjacent substituents, adjacent hydrogens, that can present a destabilizing effect that we call a steric effect. It's not quite entirely attributed to a steric effect for why this methyl hydrogen eclipsing interaction is more straining. As we start to get to see larger substituents, you'll really start to see how pronounced these kind of steric effects become. So let's talk a little bit now about steric strain and gauche interactions. And to do this, we're going to look at butane. So in butane, which is a 4-carbon chain, and we're going to look down C2C3. In butane, the eclipsed and staggered conformations are each unique. And when we have non-hydrogen substituents, such as, for example, these methyl groups are big enough that when they are close, they can bump into other large groups. We call these interactions steric interactions, which are interactions between non-hydrogen substituents occupying the same region of space. A gauche interaction is a specific steric interaction that occurs between non-hydrogen substituents separated by a 60-degree angle. This is frequently seen in the gauche conformation. In which the substituents are separated by a 60-degree dihedral angle, and the gauche conformation is generally a high-energy staggered conformation. So as you can see in this case, the two methyl groups are separated by a 60-degree dihedral angle. They are staggered, but because these methyl groups are so big, they bump into each other and introduce steric strain. So a steric interaction occurs because you have large substituents that are trying to occupy the same region of space, and they bump into each other, and that introduces a lot of strain. The gauche conformation is higher in energy than a traditional staggered conformation because of these destabilizing steric interactions. And the reason this can happen is your substituents are separated by a small 60-degree dihedral angle, so they're close enough that they can actually bump into each other. By comparison, the anti-conformation has your large substituents separated by a 180-degree dihedral angle. It is generally the lowest energy conformation as it minimizes steric strain. These methyl groups are separated by 180 degrees. They aren't close. They can't bump into each other, so we don't have this steric strain. So, with this context in mind, let's look at butane. We can separate the different conformations of butane into 4 major classes: the eclipsed, gauche, the high energy eclipsed conformation, and the staggered conformation. Now, for those wondering, how do we tell the difference between the two eclipsed conformations? For that, that's really going to depend on the dihedral angle and the exact nature of the interaction between substituents. Generally, when you have multiple substituents on each of your 2 carbons across a carbon-carbon bond, you're going to see different energy eclipsed interactions and different energy gauche and staggered interactions. Now, for butane, there are a few things that I'd like you to note. The lowest energy conformation, which we call the anti-conformation, occurs when you have your 2 methyl groups separated by a 180-degree dihedral angle. All of your substituents are staggered. The largest substituents are separated, so you don't have any gauche interactions. So this is our lowest energy conformation. If you have to take a guess for your lowest energy conformation, you're going to place your largest substituents separated 180 degrees. Rotating our carbon-carbon bond 60 degrees, we get the gauche conformation, which has this methyl-methyl steric interaction that we call a gauche interaction, specifically a methyl-methyl gauche interaction, which is about 3.8 kilojoules per mole of strain. A methyl-methyl gauche interaction, it costs you about 3.8 kilojoules per mole of steric strain. Rotating the rotating your carbon-carbon bond once more, 60 degrees, we get the highest energy or a high energy eclipsed interaction. In which case, the highest energy eclipsed interaction occurs when you have the largest substituents eclipsed. In this case, you have this methyl-methyl eclipsing interaction, which costs a large 11 kilojoules per mole. Generally, the highest energy conformation will place the largest groups across the carbon-carbon bond eclipsed. If we rotate our carbon-carbon bond once more, we get another Gauche conformation, then another lower energy eclipse conformation, and then we're back to our original anti-conformation. So again, the way to generate this graph of energy as a function of dihedral angle is you start with your two largest substituents, you place them eclipsed or anti to one another, you calculate the energy, you rotate your carbon-carbon bond 60 degrees, you observe the conformation, and you continue rotating the carbon-carbon bond sequentially by 60 degrees and calculate the total strain for each of the conformations observed. Key takeaways for butane. Lowest energy conformation has your largest substituents anti to one another. The Gauche conformation, it's still low energy because it is staggered, but it has this straining Gauche interaction between your large substituents, which introduces some strain that isn't present in the anti-conformation. There are two eclipsed conformations. The highest energy eclipse conformation has the largest groups eclipsed, in most cases. Okay, so we've seen some examples where we have stearic and torsional strain calculated. Let's talk a little bit about another way to estimate stearic and torsional strain, which are A values. So A values measure the strain for a methyl A group Gauche interaction. For example, if we look at a hydroxyl group with an A value of 2.1 kilojoules per mole, this tells us a methyl hydroxyl Gauche interaction is 2.1 kilojoules. Likewise, we look at the following Newman projection and wanted to calculate the stearic and torsional strain. In this case, we have a staggered conformation, but we have a Gauche interaction. These two substituents are separated by 60 degrees. So we have a CH3, a methylchlorine Gauche interaction. So we can use our A value table. For chlorine, this has a value of 1.0 kilojoules per mole. And that is really the only source of stearic and torsional strain in this conformation. So A values are incredibly useful as a way to estimate how much strain a substituent is going to introduce to a given conformation and to your overall structure. Given what we've seen, I'd like you to apply what you've learned to the following example, and I'd like you to calculate the total strain for this conformation, which is another Gauche conformation. And I'll give you a hint right now, there are two Gauche interactions at play here. So pause the video, take a few moments to work on this example, and then we'll discuss. Okay, so first and foremost, we have a methyl bromine Gauche interaction. This costs us about 1 kilojoule. And then we have a methyl-methyl Gauche interaction, which costs us about 3.8 kilojoules. Again, you can have a Gauche interaction between two substituents if your front and back substituents are separated by a 60-degree dihedral angle and they're close enough in 3D space to interact, to bump into each other. So adding up these two Gauche interactions, we get 4.8 kilojoules of total strain. And this is mostly stearic strain. Now, this next part is going to move into estimation, but you can estimate stearic and torsional strain given that a methyl A group eclipsing interaction is roughly 3 times the strain of a Gauche interaction. For example, a methyl-methyl eclipsing is around 11 kilojoules, which is about 3 times that of a methyl-methyl Gauche interaction. By the same token, if we wanted to look at a methyl hydroxyl eclipsing interaction, a hydroxyl group, we haven't seen that eclipsing interaction before, but we can estimate it. The hydroxyl group A value is 2.1 kilojoules. Multiplying by 3, we get about 6.3 kilojoules per mole. Now, this is all estimation, but what I want you to start to begin to understand is that if we have a gauge for how bulky, how much stearic strain a substituent introduces, we can use that to estimate the strain a substituent will introduce when it's eclipsing and when it's gauche. Importantly as well, even if you don't have an A value, you can estimate the strain introduced by a substituent by thinking about how large a substituent is and how much space the substituent takes up. Going back to how I drew the methyl group, if we compare a methyl group to a hydroxyl group, this hydroxyl group is smaller, and that makes sense why its A value is smaller, why it introduces less stearic strain and less strain during eclipsing interactions. Because the hydroxyl group just can't take up as much space as a methyl group. Generally, larger substituents that take up more space give more stearic strain. So for example, I'd like you to estimate the stearic and torsional strain in the following conformations. And I'll do the first few examples and you'll tackle the next two. So in this case, we have an alkyne. So this alkyne has an A value in our table. Let's see if we have one. So we don't have one exactly for the alkyne, but we see a nitriles there. And we know that a nitrile, which looks like this, has an A value of about 0.4. So an alkyne, which looks like this, is probably going to have an A value pretty close to 0.4. So then, for a methyl alkyne Gauche interaction, I'd estimate about 0.4 kilojoules per mole of strain. This is estimation, but you just want to get in the general ballpark for the amount of strain. And A values are a great way of doing that. Let's look at another example. This time we have a propyl-methyl Gauche interaction. Looking at the A value table, we have some values for methyl and ethyl groups. So I'd like you to take a moment and I'd like you to estimate the total amount of strain for this propyl-methyl Gauche interaction. So you may want to pause the video at this time for that. Given that a methyl group is about 3.8, an ethyl group is about 4.0, the propyl-methyl is probably going to be around 4.3 kilojoules per mole. Somewhere in that region. Let's look at now some eclipsing interactions, and I'm going to do the first one as an example. In this case, we have a hydrogen-hydrogen eclipsing interaction, which as we discussed is 4 kilojoules. We have a methyl hydroxyl eclipsing interaction, which we calculated to be around 6.3 kilojoules. And for the methyl bromine eclipsing, 1 kilojoule is the Gauche interaction multiplied by 3, gives us about 3 kilojoules of strain. Adding it up, we get about 13.3 kilojoules of steric and torsional strain. With this example in mind, I'd like you to tackle the next problem. Again, make sure to account for both eclipsing interactions, not just involving the complex substituents, but also involving the hydrogens, if the hydrogens are eclipsed. Okay, so looking in this case, we have a hydrogen-hydrogen eclipsing interaction. And we have 2 of them. 1, 2. So we have 4 kilojoules times 2. And then we have a methyl carboxylic acid eclipsing. Looking up our A value table here, a carboxylic acid is about 3 kilojoules for the Gauche interaction. So we multiply the A value by 3. This in turn gives us 8 plus 9, or 17 kilojoules of total strain. So just as a reminder, to estimate an eclipsing interaction, you can just take the A value and multiply it by 3 as a reasonably accurate rule of thumb. Now, why do we care so much about being able to calculate steric and torsional strain? Well, it's critical in order to identify the lowest and highest energy conformation. As a rule of thumb, generally the anti-conformation is going to be the lowest energy conformation, and the eclipsed conformation with the largest groups eclipsed is going to be the highest energy conformation. You will still need to calculate steric and torsional strain to verify this fact, and it's important to know how to do that, but this is a good rule of thumb. So, if we're asked to identify the lowest and highest energy conformations looking down the C2-C3 bond, first we're going to draw a Newman projection. This carbon, which is the first one listed, is going to be in the front. So C2 is going to be on the front. Everything with a wedge ends up on the right. Everything with a dash ends up on the left. This carbon is pointing down, and this carbon is pointing down. Now, with that established, here is our initial Newman projection, and let's show how it branches off into the lowest and highest energy conformation. Okay, so here we go. Here's our initial Newman projection, and as you can see, we have all of our substituents eclipsed, and we have the largest substituents eclipsed. So this directly matches the highest energy conformation. If we wanted to separate and we wanted to ensure that these methyl groups were as far apart as possible, what we're going to do is we're going to rotate this carbon-carbon bond 180 degrees so that these methyl groups are anti to one another. After rotation, this methyl group ends up pointing up to the top of the page. The chlorine ends up on the right, and the hydrogen ends up on the left. Now, there is a trick to making sure that you do not accidentally break or rearrange your carbon-carbon bonds, and it has to do with what I call the clockwise and counterclockwise counting method. If we have this methyl group and we draw a clockwise circle, we see that the order is methyl, chlorine, hydrogen. This order will always stay consistent unless you've managed to rearrange a carbon-carbon bond. So as you can see, methyl, chlorine, hydrogen. Clockwise, methyl, chlorine, hydrogen. So we didn't do anything weird. We didn't accidentally break a carbon-carbon bond. Always just make sure that your bond connectivity is retained, because if you change the connectivity of your bonds, you can end up drawing an entirely new structure. Okay, Let's do another example, this time without the Newman projection templates. So in this case, looking down the C2-C3 bond, we're going to identify the lowest and highest energy conformation. First thing I'm going to do is I'm going to draw a Newman projection. And I like going from left to right because that is just easier for me. Anything with a wedge ends up on the right. Everything with a dash ends up on the left. And these groups are pointing down because they're pointing down below the bond. So this methyl group is pointing down, hydrogen is on the right, ethyl group is on the left. I would highly encourage you to make a model in order to generate these Newman projections. From here, we have the ethyl group on the back carbon and the 2 hydrogens in the back. Okay. So, in this case, if I wanted to generate the highest energy conformation, I want my largest substituents to be eclipsed. To this end, I want these 2 ethyl groups to be eclipsed. So what I'm going to do is I'm going to rotate my structure 60 degrees. I'm going to rotate this front carbon, not 60 degrees, but in this case, to get them aligned, 120 degrees. So in this case, the ethyl group in the front now ends up pointing down. The methyl group ends up on the right, and the hydrogen ends up on the left. All of the back substituents stay preserved. This case, we have the largest substituents eclipsed. By the same token, if I wanted to get the lowest energy conformation, all I would have to do is rotate this carbon-carbon bond 180 degrees so that the 2 ethyl groups are anti to one another. So in this case, the ethyl group is drawn up top. The hydrogen ends up on the right, and the methyl group ends up on the left. The all back substituents end up retained in their same position. When you rotate the carbon-carbon bond, only change either the front or the back substituents, never both. It'll be less confusing that way. As a check to make sure that we didn't make a mistake, doing our stereochemistry check, we have the methyl ethyl hydrogen, methyl ethyl hydrogen, methyl ethyl hydrogen in clockwise order. So everything's checking out. Okay. Just one moment. So let's now try to apply what we've learned, and I'd like you to draw the lowest and highest energy conformation for each molecule across the indicated bond, in this case, the AB bond. So I'd like you to pause the video at this time, and then we'll discuss both of these examples momentarily. Okay, so let's take a look at the following example. So in this case, we're looking down the following bond. I'm going to draw out all of the hydrogens. So in this case, on our front substituent, we have 2 methyl groups and a hydrogen. For our back substituents, we have 2 hydrogens and a methyl group. Notice everything with a wedge ends up on the right, everything with a dash ends up on the left. The front methyl is pointing up, the back methyl is pointing down. Okay, so in this case, we have our methyl groups, and the methyl groups are anti to one another. The front and back methyl groups are anti. So this is the lowest energy possible conformation. You can prove this by rotating the carbon-carbon bond sequentially. So let's just show what that would look like. So for 60 degrees, if we rotate this 60 degrees, so if this is 180, rotated 60 degrees, we can have 120. I'm going to rotate, yeah, let's just rotate the front carbon. That's fine. It's not a huge deal which one you choose to rotate. So in this case, we have our largest substituents fully eclipsed. So this is going to be the highest energy conformation. Let's rotate another 60 degrees just to show. So now we're at 60 degrees. This is the Gauche conformation. The reason why it's higher in energy than the previously noted anti-conformation stems from the fact that we have two methyl-methyl Gauche interactions instead of one. If we rotate another 60 degrees, looking at the 0-degree conformation, we end up with the exact same interactions as in 120, a methyl hydrogen and hydrogen. These two structures are tied for the highest energy conformation. So we've identified the highest energy and lowest energy conformation across the given carbon-carbon bond. I'd like you to pause the video now and tackle this next problem. And we'll discuss this next example momentarily. Okay, so first and foremost, we have one stereocenter and one non-stereocenter. We're going to look down the carbon AB bond. So in this case, the chlorine is pointing up. The methylene group in this epoxide is pointing down. For those curious, this is an epichlorohydrin derivative, which is a pretty useful building block. I'm going to arbitrarily draw one of the hydrogens with a dash, one with a wedge. In this case, for carbon B, the implied hydrogen has a dash because the front epoxide has a wedge, and in the plane of the page group, this methylene group is already drawn out. Okay, so now we draw the chlorine up, one of the hydrogens with a wedge on the right with a dash on the left. The CH2 group, the methylene group of the epoxide, is drawn pointing down. The epoxide oxygen is drawn on the up and to the right because it has a wedge, and the hydrogen is drawn with a dash. Okay, although this looks a little bit complicated, in terms of visualizing it, you could really treat it like you just have an alcohol and a methyl group. Now, looking and thinking about our largest substituents, the largest front substituent is the chlorine. The largest back substituent is this methylene group. With that in mind, this conformation appears to be the lowest energy conformation because we have the maximum 180-degree separation between the chlorine and this methylene group. Let's take a look now. If this is the 180 degrees, let's rotate our front carbon 60 degrees and give us the 120-degree structure. So in this case, we have this methylene group and hydrogen eclipsed and the chlorine and oxygen eclipsed. We also, oops, this is drawn in the wrong spot, have a hydrogen eclipsing interaction. High energy, but not the highest. Rotating another 60 degrees clockwise gives us a gauche conformation. Here we have this chlorine experiencing a gauche interaction with both the oxygen and the methylene group. We call this a quote-unquote pincer gauche interaction because the chlorine is stuck between these two substituents. Generally, that gauche conformation is not commonly observed, or at least it's not going to be the lowest or highest energy conformation. Generally, you don't have to entertain those conformations as being the lowest energy conformation. Let's rotate our carbon-carbon bond another 60 degrees to give us a 0-degree conformation. In this case, we have the chlorine fully eclipsed with the methylene group and the oxygen fully eclipsed with hydrogen. So we have our largest substituents fully eclipsed. So this is about 3 kilojoules. This is about 6 kilojoules and 4 kilojoules. So in this case, this 0-degree conformation will be our highest energy conformation because it has the largest substituents fully eclipsed. While this conformation on the left will be the lowest energy conformation as it has the greatest separation between the largest substituents. For those wondering, there's a 240-degree conformation where the chlorine is in this position. The reason why it's not considered is because there'd be this chlorine-methylene gauche interaction, and this methylene group is larger than oxygen. So we want to keep the chlorine away from that methylene group, which is very similar to a methyl group in terms of stearics. Okay,